Tomorrow is April. I have no idea what's going on with the time and how the time is going so fast. It's cliche and everyone says it, but I cannot believe that tomorrow is April. March just is gone, except for today. We have one day left. April. Tomorrow is April Fool's. I will prank you. We have two things. No, we have two things to learn today. One is going to work with square roots of negatives, which I don't even remember. I should be more consistent with my algebra 1 and algebra 2, and then I could say, oh, we did this. But I think I vary from year to year. So square roots, but the inside of the square roots are going to be negatives. So when we do square roots, the number on the inside will be a negative. And that I think is probably going to be something new. So that's topic number 1 today. And then the other one will be powers of I. And you don't probably even know what I is, but you will in about 30 seconds. Go for it. I is, so I made a red mark on my note card to say, dude, say this first. So this has to go first. So actually, we're going to start with square roots of negatives, but before we can do that, you have to be aware of somebody's presence. His name is I. It's a lowercase I. Please don't be liberal with that. And you know what I is, you think? It's the square root of -1. It is called, I'll give you a name for it. It's called, you don't really need to know this. This is one of those times when it probably doesn't matter, but I'm just going to tell you what it's called. It's called the imaginary unit. And what this opens up for us is the possibility of working with square roots of negative numbers. You literally, if you understand square roots, you understand that this problem up to this point in time is impossible, right? If you understand what square roots are, you understand that what a square root means, what times itself makes -4. It's impossible because if you multiply something by itself, if it's a negative, it's going to turn positive. And if it's a positive, it's going to stay positive. So however in the world would you ever define a square root that has a negative number inside? Well, that's where this little hero comes into play, the square root of -1. So having said that, so we're going to put the powers of I on the back burner. I have no idea how long this first section will take. It really depends on how rusty or good you are on your simplification of square roots. So I am going to start the lesson with some non-negative square roots just to make sure you guys are all up to speed. So I have a list of them here just to make sure that this isn't going to be a stumbling block. So let's recall this. It shouldn't be something that you can't do because I mean we've worked with quadratics. Yeah, so like yes, you've done this. So to show my work, it would look like this. It would be the square root of and the square root of, and we would put 4 and 2 in that order, and then the 4, since it's a perfect square root, would become 2. So we would say that this equals 2 root 2, right? How about this one? How about the square root of 45? Yeah, you're pretty quick at this. I don't know if everyone's as quick as you, so you need to stop answering so I can see if everyone else in the room is as fast as you are. I don't want to get a false reading. So we would start by putting 2 blank square root signs. We would put a 9 and a 5, and then the square root of 9 is 3. So we would call that one 3 root 5. Okay, I'm going to give you some now that have more options. I think those ones were probably pretty obvious. I mean, the only other way to make 45 would have been 3 times 15, and that would be silly because neither of those is workable. So I'm going to give you some that have a few more options just to see where you're at. So how about the square root of 96? There's a lot of ways, by the way, to make 96. So in a little bit, I'm going to give you a sheet. I've given one to you before in our past together, and I do have a pile of them laying around. I got to Oh, yeah, they're over here. Uh, do you want this right now? I can pause this and get you one. Do you guys all have this still from like the past? Let me pause this and I'm going to walk around and give you guys all this. You'll find this to be useful. So hang on a sec here. So So when you look at 96 on your sheet, this will help you. Don't stop when you get to 4 times 24 because that'll be tempting because you think, ooh, 4 is a perfect square, but we can go bigger. What else do we see? 16 and 6. So this sheet will help you, but only help you with the numbers that go up to 100. So again, if you pick 4 and 24, the problem with that is then 24 has to get treed again. You never want to have to do multiple iterations of this. If you do, it's not wrong. You're making it harder than it needs to be. So if you choose 16 and 6, then the final answer is 4 root 6. And I get the question a lot of would that be 2 root 6? And the answer is of course not. Once you square root 16, it's like it's done. You can't just keep hitting a number and square rooting it over and over again, right? All right, let's do another one. How about this one? This sheet that I just gave you will not help you. Sorry, but you might know this one off the top of your head. It's just 20, right? You don't need a tree for this one because you might remember from the old days, the red list of numbers, that this is actually on the list. And so if a number is square rootable already, don't waste time making a tree. Like that's weird, right? And then the last kind of flavor of it that I wanted you to see is something like this. What's the square root of 11? It's literally root 11. So there are 3 types of numbers that you encounter. Number 1 is the kind that need to be broken down using a tree. You're very familiar with this process. Number 2 is the kind of number that's just on the list and is square rootable already, right? And then number 3 is what we call a dead root, and that's just what it is. So that's your kind of warm-up recollection. Now let's transition over into some negative. By the way, the number inside of a radical, the root sign, is called the radicand, which I know is a silly word. I'll try not to use it too much, but I will say it. So if the radicand is negative, anyone know how to proceed? It's going to involve an I, and the I is our savior here because if I need to work with square, first thing I have to acknowledge is that this is imaginary. It's within a set of numbers known as the imaginaries. It can't really exist in our normal real number definition because again, you can't square something and make a negative. It's impossible, right? So what we're going to do is we're going to treat it like a 40 in our mind. Treat it just like a 40. Forget the negative for a second. How would I tree down a 40? 4 and 10, right? So I would put 2 blank roots. I would put a 4 and a 10. And my answer at this point would be 2 root 10. But in order to account for the fact that the radicand was negative, all you simply have to do is put I right there. The I needs to be in a very specific location, and you'll learn this probably within the next few minutes, but if not, you'll just learn through experience. First thing I want to say is I cannot go at the back. So this is an unacceptable answer, what I'm about to write. Why do you think mathematicians don't accept this? Yes, but that's perfect answer because we don't know if I is in the square root or not. So I is never allowed to go after a radical because we're not sure. And like in mine, it's pretty obvious that it's not, but you'd be surprised how many times people get close and then you're kind of like, oh, it's getting closer. I don't know. So to take that even off the table, we just don't allow I to go there. I will always go before the radical, never after it. Okay. All right, let's do another one. How about the square root of negative 12? It's a perfect answer. 2i root 3. And at this level, like if you were algebra 1, I would require you to show the trees. Like at this point, we've done this before. So if you can do the trees in your head, I'm not going to balk at that or complain about that. Where I'm going to get
Please
crabby,
excuse the interruption. If you're going to LCCC this morning, please head to the comments now. Thank you.
where I'm going to cloud up and rain on you is if you put this answer. This answer will get you yelled at, okay? And again, I've got no issues with you bypassing and doing things in your head, but you have to remember that it's never felt 4 and 3. Like it started as a root 4 and a root 3, but this is the answer that'll get you kicked out of class. So again, save time if you want to, just don't do anything stupid. How about the square root of negative 48? So using your sheet, what's the most attractive factor pair of 48? 16 and 3 is our biggest biggest money maker there. So we tree it into 16 and 3. Make sure you keep roots on those initial ones, even if it's in your brain. What do we wind up with? 4i root 3. Good. How about this one? How about the square root of negative 10? No, it's dead. Almost dead. So 10 is one of those trickies. There's like 30 is another trick number that feels like you should be able to tree it. Just because 2 and 5 go into 10, we don't give any rips at all because 2 and 5 are both trash, right? I'm only interested in numbers that are square rootable, and 10 contains nothing. So all we can do to fix this is to take the negative out and write it as I root 10. That's part of the simplification process right there. Just getting the negative out. Right? How about this one? How about the square root of negative 64? It's perfect. And so what I wanted you to learn from this example is that the I, if there's not a radical, by the way, we all agree that 64 is not one that we make a tree. You're not sitting here scanning this sheet and thinking about factor pairs. That would be really kind of not very not efficient, right? We know 64 just turns into 8. It's square, right? So we get 8, but then you put the I after the square root. You do not want to put I8. That'll get you laughed at. So we put 8I. What you learn is that the I always goes after the rational number, but before the irrational number. If there's just one, put it in the right place. If there's two, sandwich it in between. And then the last one is a little bit tricky, and then we'll get to the second half of this lesson. The only way to be miserable today is if you just have always struggled with simplifying roots, then you're in for it, but it is what it is. So our sheet doesn't help us here. Calculators do. And those of you that have more powerful mental math abilities, you'll just be quicker at this. So sometimes life's not fair, but that's how it goes. There's a nice pair that makes 192. And it's okay. There's no shame in having a calculator and just experimenting with it. Like first thing I would do if I were in your seat is I would try dividing it by 2. Because I know I can, and I'd get 96 and 2. But I wouldn't like that because 96 is not on the list. But there's another pair. Right. And again, it's just you and your calculator just sitting down and having a good time together. And you figure out that 64 times 3 makes 192. And you can arrive at that a couple different ways. You can try dividing by square rootable numbers, or you can try dividing by little baby trash numbers like 2 and 3 and 5. And sometimes when you divide by little meaningless numbers, the other number in the division problem comes out to be a very meaningful large number. So you don't always have to sit and be a slave to the 4, 9, 16, 25. You can divide by little numbers and sometimes find what you're looking for. Perfect answer. So what would the final answer to this be? Perfect. 8I root 3. So again, the I will go between the rational number. 8 is called a rational number, and the root 3 is called an irrational number. Make sure you tuck I right where he's supposed to go. So the first half of your assignment will involve that. Do you have any questions or issues with that? Okay, the second part of this has potential to be confusing, so you gotta, as always, just advocate for yourself and don't assume that if you have a question that you're the only one and that people are like going to think you're dumb. This part can be a little bit abstract at first. So what we're going to do is we're going to look at different powers of I. So we all know that if you take I and raise it to the first power, you just get I. What we're going to do is we're going to work our way down the list now, and we'll have some, I hope, intelligent conversations about what's about to happen here. If we take I and raise it to the second power, anyone want to take a guess at what we get? Say again? It is I times I. So maybe this is a great time. I wasn't sure how you'd answer that question. So your answer tells me we need to show some mark. Let's show some mark. This is what I squared looks like. I times I. But we know what I is. What is it? It's the square root of -1. So if I write out I times I, it's actually the square root of -1 times the square root of -1. And in math, what happens when you multiply a square root by an identical copy of itself? The roots cancel, and what do you get? You get, how about this? The square root of star times the square root of star is just star. The square root of 5 times the square root of 5 is just 5. So you just get -1. So you can add now to your little table that we're constructing over here on the left that I squared just equals -1. So we now have two facts. I to the first power just gives you back I, of course. I to the second power returns a -1, which, I mean, that statement right there really hits at the heart of the imaginary number system. Like, holy crap, I just squared something and got a negative answer. That's funky. Yeah. How about I to the third? I've taught this lesson dozens of times, and every time I would have you, in this case, think about pairs that you are, things you already know. And so if you know this, I'm going to let that sit there for a second until you hop on board. You would agree, just using basic properties of exponents, that I to the third is I to the 2 plus 1, right? But we know now everything that's on the board. We can use prior knowledge to build new things. And so I to the third is just I to the 2 times I to the 1, because 2 plus 1 is 3. Well, do we have a value for this red thing? What is it? It's -1. We just learned that. And do we have a value for this yellow thing? It's I, right? And what's -1 times I? -I. So we now know that if we take I and raise it to the third power, we get -I. The fourth one is the one I consider to be the most interesting. The others might be a little confusing to you right now, but eventually this will all just be like a new language. It's no big deal. I to the fourth is interesting. If I build I to the fourth, I can build it out of an I to the 2 times another I to the 2. Because again, we all agree that 2 plus 2 is 4, right? But again, we have values. We have prior knowledge that we can use to carry ourselves forward. What's I to the 2? It's -1. We know that from 2 lines above. And what's I to the 2? And what's -1 times -1? So we can now add to our repertoire that I to the fourth power equals a very real number, +1. Now, something interesting is going to happen here. And if you don't think it's interesting, that's okay. But I hope that eventually you will. We're going to continue the cycle now. And you can continue working downwards. I don't care about the formatting of how you do this. But I am going to write I to the fifth over here. And you'll see why momentarily. This is your first real chance in math to see some like modular sort of arithmetic idea that there's a repetition that's about to commence. So I to the fifth, you would agree, can be broken down into I to the fourth times I to the first. Because again, if I hope I haven't lost you, just basic rules of exponents, right? Any exponent can be rewritten as the sum of two other exponents. 4 plus 1 is 5. But we know now, we have prior knowledge. What's I to the fourth? What's I to the fourth? It's 1. And it's the great non-changer. 1 steps in and says, I will not change anything. I am like your rock. It's called an identity. In math, 1 is called the multiplicative identity. He says, multiply me by anything. I'm not going to change anything. And we know what I to the 1 is. What's I to the 1? It is I. And what is 1 times I? I. So I'm going to erase my work. And next to I to the fifth, I'm just going to put I. And you see now why I decided to write it next to I to the first. And if you're really paying attention, you already know the answer to this, but I'm not going to assume that you do. That would make me a bad teacher. I try not to be. So let's do I to the sixth. What's a great way to break down I to the sixth? It is. You could do 3 and 3. I personally will always take advantage of I to the fourth. So that's, you could do 3 and 3, Jordan, and it will work for you. I like I to the fourth though, because it's I to the fourth is my favorite because it's just 1. So I'm always going to dip that one in there and shake a big chunk out. The identity. What's I to the fourth again? This is 1. And what's I to the 2? -1. And what is 1 times -1? So we can now say that I to the 6th power is -1. And again, if you're paying attention here, you should be noticing some similarity between these as we look sideways. This is a cycle. It's periodic. What's happening is every 4 terms, if you will, in this sequence, the pattern has to repeat itself. And the reason is because if you take out a chunk of 4, that multiplicative identity just keeps taking you back to where you were. And I'm going to do it just because it's my job, but you already kind of know the cat's out of the bag. I to the 7th could be broken into I to the 4th times I to the 3rd because, well, 4 plus 3 is 7. And again, third verse, same as the first. What's I to the 4th? 1. The great identity, 1. And what's I to the 3rd? And what's 1 times -I? Therefore, we, as we would have surmised, can say that I to the 7th power is equal to -I. And then, of course, what's I to the 8th? We know it's going to be 1. Let's just verify that. That's going to be I to the 4th, our favorite, times I to the 4th, our favorite. And what's I to the 4th? 1. What's I to the 4th? What's 1 times 1? And what happens now is the pattern repeats again. So we could make another column of the table. And we can jump again to another multiple of 4 plus 1. And that's going to be obviously I to the 9th power. I to the 9th is just I to the 8th times I to the 1. What's I to the 8th? What's 1 times I? And as we would have surmised, then we get I. Is anyone failing at this point to consider or see the pattern that every 4 we're returning to the beginning? Okay, so if that part makes sense so far, what we're going to do now is we're going to take a leap of faith at this point in time, and we are going to jump ahead and we're going to ask a question like this. What is I to the power of 135? As always in a case like this, we don't want or have time to go through and find all the powers of I up to 135. So we're going to use something called modular arithmetic. We're going to consider the fact that this has something to do with the number 4, right? So what I'm going to do, and your calculator can do this for you, I'm going to do these first ones by hand just to show you, but you're going to take the number 135. We're going to go old school. We're going to divide by 4. Why 4? Well, because there's 4 terms in the pattern, of course, right? So however long a pattern is, you divide by that. And since there's 4, well, there you go. And the math, you remember this from the old grade school days. You go, okay, 4 goes into 13 3 times. 3 times 4 is 12. 13 minus 12 is 1. Drop the 5. 4 goes into 15 3 times. 3 times 4 is 12. And this number that I'm writing in purple is very important. 3. What is that called? It's called the remainder. In a long division problem, a remainder is pretty important stuff. So what that's going to do is it's going to point us back to a very particular place in our original table. So remember that for this I to the 135th power, we're thinking, okay, R equals 3. And I'll show you how to do that on your calculator here in a little bit. So I'm going to get rid of a whole bunch of my work up here. I don't need all this. You would all agree that if you took this number and divided it by 4, the one I just circled in red up there at the top, that 1 divided by 4 is 0 with a remainder of 1. You would also agree that if you took the number I just circled in green and you divided it by 4, you would get 0. 2 goes into 4 0 times. Did I say that right? 2 divided by 4. 4 goes into 2. How am I trying to say that? Anyways, it's 0, but what's the remainder? 2. If you take this yellow number 3 and divide it by 4, what's the remainder? Now, watch out, because you're going to want to answer this question in the wrong way. If you take this number 4 and divide it by 4, what's the remainder? It is 0. There are only 4 possible remainders that can happen when you divide by 4. If you ever say the remainder is like 4 or 5, you don't understand division just because, like, if I say 12 divided by 5 and you give me a remainder bigger than 5 or 5, then I say, no, 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 you didn't get enough out. The remainders are either 1, 2, 3, or 0. So all we have to do when we want to find a large power of I is look back into our table and understand where it points us to. For I to the 135th power, what again did we get as a remainder? What's the answer? Then the answer is negative I. The remainder will point us right back to one of those 4 key components for this repeating pattern. And you can do that for any power of I. I can make it very large and we're not scared. I could do I to the power of 1,342. Not scared. So I'm going to go do some old school, like grade school division here. Bust out the long division. And then, like I said, I will probably show you after this how to do it on your calculator. I'm going to take 1,342 divided by 4. And here we go. How many times does 4 go into 13? 3 times 4 is 12. Subtract 13 minus 12 is 1. Drop the 4. Used to do this back in grade school. How many times does 4 go into 14? 3. 3 times 4 is 12. Subtract 2. Drop the 2. How many times does 4 go into 22? 5 times. What's 4 times 5? 20. So you write the 20 in there. Subtract. What's the remainder? 2. So all we have to do is go back to our OG table and figure out where the remainder is 2, which is right there. So what's the answer? Negative 1. Let's talk real quick about what remainders look like on calculators. Everybody, if you have a calculator, if you don't, it's okay. No problem. But take on your calculator and type, if you probably don't need it for this, it's a little embarrassing for some of you that I'm saying this, but what's 1 divided by 4? No, it's 0.25. So 0.25 on your calculator, whenever you see any number that ends with a 0.25, that's a remainder of 1. That's what the calculator is trying to tell you, is your remainder is 1 out of 4. That applies to huge numbers. If you type anything that's not a decimal, anything into your calculator divided by 4, it will end with either no decimal, a 0.25. This other one, what's 2 divided by 4? 0.5. That's the other one you might see. And that's your calculator trying to tell you that the remainder is 2. What's the only other thing that can happen when you divide by 4? 0.75. Good. So if you take 3 divided by 4, you get 0.75. And that's your calculator saying, hey, homie, the remainder's 3. And what happens if I get no remainder? Like if I do 4 divided by 4, what do I get? I get no remainder. So whenever you get no remainder, then you're at the end, if you will, of the cycle, the 4th term. Any questions about that? Okay, then the last little bit of this is problems like this. I didn't teach this one year, and then they were like, oh my God, what happened? And that was my bad. So let's do like I to the 4th times I to the 31st times I to the 99th times I to the 20th. Oh, Dios mio, whole bunch of I's here, right? How do we figure out where we're headed with this? Add them together. Good job, Kane. Like some people say, well, I could just go through and do each one. Yeah, those people, phew, that's loco and la cabeza, man. Use your properties of exponents. What's 4 plus 31? What's 35 plus 99? That's 134 so far. And what's 134 plus 25? 159. So this problem really is just asking you for I to the 159th power. And if you want to, grab a calculator and type it in. You're going to type into your calculator 159 divided by 4. Every time it's 4 because the pattern is exactly 4 long, right? So when we're working with powers of I, the division will always be by the length of the cycle, which is 4. You got 39 point what? 39.75. The remainder is then 3. So we go to our table where the remainder is 3, and we say, what is the answer? Negative I. So the answer to this problem is negative I. you have any questions about that? There are two sections to the Delta Math today. I decided to just do them both in one day because this is another thing we have to talk about before we can finish quadratics unit. Section 1 is just going to be a whole bunch of the square roots like this, where you break them down, and that's all. And then section 2, I believe, is all multiple choice. There are only 4 answers you can get. So your problems are going to be like option A is like I. Option B will be like negative I. Option C will be like 1. And then option D will be negative 1. Like those are literally the only 4 answers in the world when you're working with powers of I. So that's why they decided to do it as multiple choice. I only gave you 1 attempt on these because if I gave you 4, that would be really like dumb, right? So multiple choice, I want you to get them right on the first try. The first section, you have 2 attempts, so you can miss once, but I still don't want you to. So that's that. It's in the Delta. We don't have a ton. We got like 9 minutes. It's a lot, kind of, but not enough. So we'll probably continue this tomorrow. In the meantime, let's have 8 really good work minutes here
Can you
today. Sure.
like work on doing that?